hello everyone. So today we have this linear algebra problem, which is finding a matrix for a linear transformation. So we're asked to find T, B, B prime, and I'm reading that from right to left. And that's usually how you read that for our transformation T, going from the space of all degree 1 or less polynomials, that's P1, to P3, which is the space of all degree 3 or less polynomials over the real numbers here. And the transformation is defined as T of P of T equals T squared plus 1 times P of T. So essentially you take your polynomial degree 1 or less, when you put it into your transformation, you multiply it by T squared plus 1, and that results into a polynomial of degree 3 or less, okay? All right, and then we have two bases here. B is 1 minus T 3 plus 14, that's a basis for P1. And then we have B prime, 3 minus T, 2T plus T squared, 5 plus T squared, and T cubed, which is a basis for P3. Okay, so how do I find this matrix? So here's how let's go straight to it. Here's the solution. You're gonna compute the transformation acting on the basis vectors for your domain. So our domain here was P2, okay? P1, excuse me. Domain was P1, and the basis vectors were 1 minus T and 3 plus 4T. And yeah, whatever the basis vectors are for your space, you will find the image of those basis vectors. So if you plug 1 minus T into your transformation, you can take 1 minus T and multiply it by T squared plus 1. That'll come out to be 1 minus T plus T squared minus T cubed. If you put 3 plus 4T into your transformation, it's going to result in 3 plus 4T plus 3T squared plus 4T cubed. It's essentially just foiling here. Okay. So now, once you get the image of each of those basis vectors for your domain space here, you're going to write the results as a linear combination of the basis vectors for your range space. So the basis B prime was 3 minus T, 2T plus T squared, 5 plus T squared, and T cubed. So I'm going to write each of those images that I just got in terms of these vectors right here. So first image was 1 minus T plus T squared minus T cubed. That's equal to, I'll just call them C1, C2, C3, C4. C1 times 3 minus T plus C2 times 2T plus T squared plus C3 times 5 plus T squared plus C4 times T cubed. Okay, so that's what we have. Now, in order for me to solve for these constants we're trying to do again, I'm going to have to simplify this a bit. I'm going to apply a little bit of algebra to distribute and such, and I'm going to be adding like terms or putting like terms together here, okay? And that'll make a little more sense here. So what I did here was I distributed the C1, C2, C3, and then I added everything that has, and that's what you see here. And then from that step to the next one, I put all the constant terms together, all the coefficients of T, all the coefficients of T squared, and all the coefficients of T to the third. Why did I do this? Because on the left-hand side of that equation, the last equation, I have a polynomial, 1 minus T plus T squared minus T cubed. And if I have that polynomial set equal to that equation, the only way this is going to work is if the coefficients of that polynomial here on the left-hand side equal the coefficients of the polynomial that I have on the right-hand side. So yeah, when we have the 3C1 plus 5C3, the negative C1 plus 2C2T, etc., those are coefficients of this like polynomial of degree 3 as well. And in order for those two polynomials to agree, you have to set the coefficients equal to each other, okay? So the coefficient for your constant is 1, that has to equal 3C1 plus 5C3, so right here. Coefficient for minus T is minus 1. That's got to equal the coefficient for T on the other side, minus C1 plus 2C2, and etc. You would have 1 equals C2 plus C3, and minus 1 equals C4. Now, you have that system, and instead of just solving it, let's look at what you have to do for the other set of polynomials. You pretty much do the same thing here, okay? You'd have 3 equals 3D1 plus 5D3, 4 is minus D1 plus 2D2, 3 equals D2 plus D3, and 4 equals D4. Okay, so I didn't do the arithmetic there like I did before, but it would come out to be the same. And if you notice here, you have the equations, the variables that you're working with, your equations have the same coefficients essentially here. So if I were to solve the system of equations, yeah, I could do this for both separately, but I could basically combine them both because these equations have the same coefficient. So you're just showing your work here, okay? And that's what we did over here. So you would go ahead and make, again, in this case, a matrix with your coefficients coming from here. Again, that's the same thing if you use the ones with the C1s and the C2s and the C3s. And yeah, you set them equal to the 3, 4, 3, 4, and then -1, -1, -1. That's what you see here. And essentially what you do is you solve. Okay, so at this point, this is something you've already learned in your class in terms of solving a system of equations with row reduction and all. And after you row reduce, you get the identity matrix, and that always will happen, by the way. You should always get the identity matrix on one side. If you don't, that means you did something wrong, so go back and check. And you'll have a solution here for your matrix, which is everything that's on the other side of the identity matrix. So you have that right there, okay? Now, why do we compute this? Why do we care? When you compute the matrix relative to a transformation, you can compute the images under a transformation instead of directly with a matrix, and that simplifies things a lot sometimes for us. Okay, so that's why you do that, and we will be, we'll link a video to an application of this, of finding an image using this matrix. And yeah, if you had seen my previous video, I talked about that as well, so I'll link that, and thank you for your time.